Okay, so let's start. So last time I formulated the Lefschetz trace formula with finite coefficients. We proved some properties of traces, namely the additivity. So it remains to prove the formula. And the proof will be done by reduction to the case first of local systems. And then we'll use the fact that any local system with finite coefficients becomes trivial after a finite Tal cover. And then we ultimately reduce the formula to the case of trivial coefficients, which is true by a theorem of Weil. So the proof is kind of similar to the one that I gave for QL coefficients. Remember that we had a very simple argument for QL local systems that are Artin local systems, such that the representation of the fundamental group factors through a finite quotient, meaning that a local system becomes trivial after a finite extension. So, but in that proof, we use some there were some denominators in the argument. So we used some projectors in the group algebra. And so to write them down, you have to divide by some integers. So what we gained by looking at finite coefficients is that now every representation is Artin. It factors through a finite quotient. But what we lost is the semi-simplicity, right, of the group algebra of a finite group, right? We no longer have these projectors. So we have to be a little careful here. And so the first part of this lecture will be a discussion of, well, divisibility property of traces. So properties of traces. Well, this will be kind of a series of lemmas, each of which is sort of a easy direct computation. But in order like to give you an idea of what we want to show, I will kind of make a claim. So I will prove it even in a more general statement, but this will explain what we need. So suppose I have a finite group, G. So its number of elements is finite. And suppose P is a, yeah, and so also I need a commutative ring. Oh, sorry. Ring. And suppose I have a projective finite projective lambda G motive. And let F be its endomorphism. Then I can take the trace of this endomorphism in P. And, well, think of, for example, you may let's even assume that, say, it's free over, well, it's projective over this guy. In particular, it's projective over lambda. So this trace is well defined. I take the trace over, let's see how I want to. I think of this as a projective module over lambda. Think of lambda, in our example, lambda will be just z mod L to the nz. So you have a projective representation of a finite group, say, on a free module over this guy. And you can take the trace of an endomorphism of this. And I claim that it's divisible by the order of the G. Let's see what it means. For example, you can take for F. So F is, let me make it more precise. So what I really mean is that it's endomorphism of P over G, right? So you can take for F, for example, the identity endomorphism. Then what is the trace? So think of, again, imagine that P is a representation of G on a free module over this guy. Then there is a notion of dimension, right? It's free, so it's rank. So the trace of the identity endomorphism is just the dimension, right? So my claim is that the dimension of any representation is divisible by G. It looks stupid. For example, you can take the trivial representation, but it's not projective. So if representation on a free module over this guy happens to be projective as a module over this, then it's dimension in lambda, right? This is if say this L is relatively prime to the order of G, there is no claim at all, right? Every element of lambda is divisible by G. However, if, say, L divides the order of the group, then we know that somehow there are many representations. The category of representations is not semi-simple, right? Take even more, take n equal 1, right? And assume that L divides G, order of G. Then the claim is that any projective module over G has dimension divisible by L. This is not a terribly difficult statement. It reduces to the case when G is Z model Z, because every G has a subgroup isomorphic to Z model Z. And then the claim is that if you have a projective Z model Z module, projective representation of Z model Z, then its dimension over a finite field of L elements, then its dimension is divisible by it. So only regular representation is projective. Okay? So that's kind of a type of statements we are interested in. I will give a proof. So the proof, so let's fix some, so the proof is based on, again, the proof is based on the following construction. So again, lambda, for this lecture, lambda will be always commutative. Ring. So G is finite group. So define. So I want to construct, I call that for any ring. For any ring, we have the notion of its Hochschild homology. We called it, we denoted lambda bmol, lambda G bmol, and this is nothing else but the quotient of the ring modulo its commutator. Subgroup lambda G, lambda G. Okay? So where does it come from? Well, what is the role of this? So if I have a projective module over any ring and endomorphism of this module over this ring, then there is a well-defined notion of a trace. which lives in this quotient. In order to prove this claim, I will compare two traces. I can think of P as a module over this, and F as an endomorphism over this ring, and can take the trace, which will be an element of the Hochschild homology of this ring, right, in this quotient. Or I can think of P just as a module over lambda and take the trace there. It will be an element of lambda. And I want to compare these two. And the divisibility will come from that, right? So let's think what this quotient is. So who remembers group theory? Or, well, theory of elementary kind of representation theory of finite groups. What are, say, function homomorphisms? Well, what is this?
Looks like lambda of idealization.
Lambda, is it really true? So let's think let's think what is a homomorphism from this guy to some abelian group, or some lambda module, say.
It's a class function on G.
Right, it's a class function on G. So it's not at all abelianization. So it's a homomorphism. This is a lambda module. A homomorphism from this guy to any lambda module is the same as a map from G to this lambda module M, such that G1 times G2 and G2 times G1 goes to the same element, right? Or equivalently, that means that that's a class function on G with values in M. So, lambda module such homomorphisms phi are in one-to-one correspondence with class functions. Right. So in particular, I have a very nice class function. So let's take consider this. Epsilon. Let's consider the following class function. So epsilon of sum of a lambda lambda G is equal to lambda E, where E is the neutral element. Right? That's definitely a class function. So it's equal to 1 on all conjugacy classes except for the class of E. And therefore, it factors through this group. And I will denote this by epsilon. So now I have lemma. So, okay. So P finite projective lambda G module F endomorphism of P over lambda G, then I have, we can do two things. We can consider its trace of this endomorphism, where P is regarded as a lambda module. Or I can take the following, I can take the trace over lambda of G of the same endomorphism. So what I get is an element here, and can apply epsilon to this. Okay. And now there is a question to you. What is the difference between these two numbers? I want to compare. Now they, once I apply epsilon, they live in the same ring.
So if one of them was order of G times large, then we prove the claim.
Yes. So, okay. So let's give an example. Let's consider an example. Let's take for P just this guy. That's definitely a projective module. What are endomorphisms of a regular representation, of the regular representation?
Just multiply by any element.
Right. So if you have any ring, and then this ring, view it as a left module over itself, the group of the ring of endomorphism of a regular of the free module over a ring is the opposite ring, right? In the case of group, the opposite is the same as the original, right? So just write multiplication. So what we are doing here, so here we take the character of the regular representation, right? F is an element of this group algebra, and here, well, so F is just an element here. So we are taking the character, and here, well, we take basically F itself, and then apply epsilon. What is the character of the regular representation? So maybe I will. Okay. So my claim is that the answer is this, and this will prove the claim. And let's prove this. So well, any module. So what is a trace of a projective, of an endomorphism of a projective module, right? So by definition, a projective module is a direct summand of a free module. So you can find another module, P prime, such that this is lambda free module. Okay. And so here, if I have a endomorphism F, I can construct an endomorphism of this guy simply by defining it to be 0 on the second summand. And by definition, the trace of F on P is the trace of the matrix. So you consider F, 0. You think of this as, you write it as a matrix. It's a free module. And, okay, and you take the trace. And then you project it to this portion. So it follows from this that it's enough to, we may assume that our P is just the free module, right? And then every endomorphism of every module is given by a matrix, and both sides depend only on the diagonal entries of this matrix. So without loss of generality, right? Trace depends only on the diagonal entries. So, so we may assume that P, this reduces the proof to, well, the case when P is lambda G. So then if is right multiplication, by some element f lambda G. So let's compute the trace. Yes, and by the way, in order to prove the claim, I need to put G here. Sorry for this. Right? That's what I need. That is what is due. Okay, so let's do the computation. So let's compute the trace of f acting on lambda G. So this is equal to the sum of traces of, it's equal to sum over elements of G, lambda G, times trace of G, acting on the regular representation. And what is this? This is equal to lambda E. Is it true? Well, if G is not the natural element, then the trace is 0, right? Because in the standard basis, this matrix has no diagonal entries at all. So only G equal to E contributes. But then you're computing the trace of the diagonal matrix, but this is order of G times order of G matrix. So it's you get this. And this is precisely epsilon applied to F. Times order of G. So we get the formula. So very good. So we define trace for a projective module over the group algebra. We define this trace to be epsilon of trace over lambda G of F P acting on P. That's the quantity that appears in this lemma, right? With this notation, the lemma asserts that if you multiply this guy by the order of the group, then you just get trace of F acting on a projective lambda module. So we have a refined version of the trace. Good. Now I will need some properties of this refined trace. So first of all, so here is lemma. So let P be a finite projective lambda G module. And let M be lambda G module finite projective over lambda. So it's a representation of G on a lambda module on a projective lambda module. Then if you consider the tensor product of P and M over lambda, this is a finite projective. Lambda module, lambda G module. Right. So you can take the tensor product of representations and then claim that if you tensor a projective module with any module, you get a projective module. How to prove this? What happens if you take, for example, a regular representation and tensor it with any other representation, M? What do you get? Let's think about even complex numbers. Let's take a representation of our complex numbers of a finite group and tensor it with a regular representation. Does it depend on the representation you start with? What is C of G tensored with V, where V is a representation? I claim that it depends only on the dimension of V. Просто несколько копий. Okay, so I claim that this is true. This is equal to C, canonically C of G, tensored with trivial. So what is it? So here V is any representation, and G acts diagonally on the tensor product. And here I consider V as the trivial representation, right? I let G act trivially on the same vector space. And I claim that these two guys are isomorphic. Well, indeed, this is a free module over C of G. Given a homomorphism from a free module to anything is the same as given a homomorphism of vector spaces from this guy to this, right? Because any homomorphism from a free module is determined by what it does on generators. And of course, there is a identity homomorphism from here to here. It's vector spaces. And this gives me a homomorphism of C of G modules, which happens to be an isomorphism. Use the inverse. So the same is true over any lambda. So you can use, for example, this argument. Let me write this down. So proof one. is the following. So P tensored with M or lambda is isomorphic to P tensored with lambda. So I replace M by trivial representation. So it's this. Что? So it's the same lambda module, but with trivial action of G. And then it's so M is a direct summand of free lambda module, right? Because it's projective over lambda. So this guy becomes a direct summand inter P, direct sum of several copies of P. Okay? So this is first proof. Second proof, you can check projectivity directly by looking at morphisms. You need to take home over G from P tensor M to any n. This is over lambda, and observe that this is the same as home from lambda G over lambda G from P to home over lambda from M to N. So now projectivity means that this is an exact functor, right? The functor that takes M to this home is exact. So this is an exact functor because M is projective over lambda, and this is an exact functor because P is projective. Essentially, these are the same. So now I need another lemma. Suppose we are in this situation, and I give you an endomorphism lambda G of P, and another endomorphism of say M. Then I'm looking at traces. I'm looking at these traces, refined traces, right? So I want to take V, U tensor V acting on P tensor M over lambda. So what is the trace of tensor product of two matrices? What is the trace? What is the character of tensor product of representations? Product. So I want to have this property for refined traces, and that's what it means, right? So recall that informally this refined traces is just the usual trace divided by the order of the group. So if order of the group were invertible in lambda, then this formula is just a corollary of the well-known property of matrices. So, right? So here you divide by the order of G, and here you also divide by the order of G. And here, this is the usual trace. That's because the only thing that makes sense, right? M is not free, is not projective over G. So the proof is done by reducing to the case when P is free module. And then And then this is a kind of direct verification. Again, the motivation for this is that it's obviously true after multiplying by the order of G. So now need some more lemmas. Now I will consider the following situation. So maybe let's make a definition. So a monoid extension of n is a monoid of natural numbers, positive integers of n by a group G is well, an extension of groups. So let's call it gamma. That's a group extension such that gamma is pre-image of n sitting in Z, right? So you have gamma here, you have n. So what are extensions of Z by G? So any such extension is a semi-direct product, right? So it's determined by so these extensions are classified by automorphisms of G. So you just need to know how this generator here commutes with G. And
N is a subset of Z. What is that?
N is the set of natural numbers.
Oh, it must be N.
Wow. Okay, so so gamma is a monoid. So you can multiply elements there, but you cannot divide them in general. But in any case, you can form the group, the monoid algebra, right? You can take lambda of gamma. That's a ring. It's an algebra. So so here is the lemma that I need. Okay, notation. So for gamma in gamma, I will denote by Z gamma all elements, the group of all elements in G that commute with this gamma. Gamma G centralizer. So G gamma. That's a subgroup of G. And now I have the lemma. So let P be Z lambda gamma module. Finite projective over the subalgebra here. Okay? So, and what I'm interested in is the trace of over lambda. Well, And take P, and so P has an action of gamma. In particular, for any gamma, I can take the trace of gamma acting here. And my claim is that this trace is divisible by the order of this group. Namely, that it's equal to order of Z gamma multiplied by the trace, by this sophisticated trace, refined trace, Z gamma okay, what's lambda? Gamma acting here, right? And this should be obvious because, of course, gamma is not an endomorphism of representations of G, right? Gamma need not commute with all elements of G, but it definitely commutes with elements here. So I can think of gamma as endomorphism of P in the category of representations of this group. And then this is a corollary, well, of the lemma that we had earlier. So, so that's okay. So I need two more lemmas. They all sort of not very deep. Okay, so lemma. So suppose I have P is a will be lambda gamma module finite projective over lambda G. And need another module, M, which is module finite projective over lambda. Projective over lambda. Okay? So I'm interested in the trace in the Tesla product. So P M so this has a diagonal action of gamma, and so I'm interested in this refined trace, and I claim that it's equal to the refined trace of gamma acting on P times the usual trace of gamma acting on M. And again, this is a corollary, I think, of this property. Now, here is the main statement that I will need. So suppose I have P, which is lambda gamma module. Finite projective. Finite projective over lambda G. And what I want to do, I want to consider its coinvariance over G. So this is just defined to be the tensor product, right, with a group algebra of P. And then, so the main formula is the following, that the trace of identity, this identity is an element of N, which is gamma modulo G, acting on this coinvariance is equal to the sum over all conjugacy classes. So I look at all gamma in this monoid, right? This is an element in N. And I consider these elements up to conjugation. So this means that sum over G conjugacy classes. All right. So I consider preimage of 1, right? So here, and G acts here on this preimage by conjugation. And so I take the following, the traces of this defined traces of gamma acting on P, right? So that's the main formula. So instead of, so let me give you a proof of this identity after multiplication by the order of the group. I need precisely the formula in this setting, but the proof will be kind of more illuminating. Well, I will explain what you will have to do in order to prove the refined version. But let's first see why this is true. This is easy. Okay, so proof after multiplication by order of G, right? So let's see, what is the order of G multiplied by the trace of this operator? Yeah, maybe, I hope it's clear. So P has an action of the monoid gamma. When I take coinvariance, this action reduces to the action of the quotient. So I have one well-defined element here. So this is also well-defined, right? Because so if you replace lambda by a conjugate element, the trace will not change. So let's take this trace And let's first observe that let's write it as the sum over all gamma mapping to 1 trace of lambda of gamma on PG. And right. I hope it's okay. So why that? So in fact, here I take in some of the same guys, right? Because G does not act here. This gamma, action of gamma on the coinvariance does not depend on the choice of preimage. So I have, that's clearly the same. So now maybe let's, sorry, I want to write it as a trace of this gamma on PG. And now I claim that this is the same as trace of the same operator acting on P itself. In fact, if you think about this operator, what is this sum, right? You take all preimages, you can take first one preimage and then multiply it by the sum of all elements in the group. And so this map is sort of the composition of the projection from P to PG and composed with this operator. So formally, you can derive it as follows. So you have PG, this invariance. It sits inside P, and you have coinvariance. And there is a canonical projection from invariance, from P to coinvariance. So let's call this A, and this call B. And now I also have this map, which I call C, and C is sum over all gamma, all preimages of 1 of gamma, right? Clearly, if I take any element of P and I apply this sum, I get an element which is invariant under G. So, and what you have to use is that trace of A, C, B okay, so you go this way, is the same as trace of, well, you need to take cyclic permutation. B, A, C. So if you do this, you get the trace on P. If you do this, you get trace on PG. Okay? And now so what remains to do? So you just have to observe that the trace of gamma acting on P. So again, conjugate matrices give the same contribution, right? So that means that I can write it as a sum over conjugacy classes of these guys, and this is the trace of gamma epsilon, and this gives me order of G times the sum times the sum that is written here. Raise lambda z gamma gamma epsilon b. Okay? So again, that's not a really complete proof because I only proved it after multiplication by G, but I think I don't want to say more about this. Instead, I want to explain kind of maybe a geometric meaning of this formula, right? So try to give an application. Or example. So okay. So let's consider. This is an example. Let's consider an étale, a finite étale, group scheme. Over F2. What is this? So a finite étale group scheme of an algebraically closed field is the same just as a discrete group, a definite group, right? You take its F q bar points. So if you have a finite étale group scheme over a non-closed field, so let's say G underlined. Then you can take its F q bar points, and you get a finite group, but it comes together with an action of the Galois group of F q bar over Fq. So, and this gives you an equivalence of categories between the category of finite étale group schemes over this, and the category of groups equipped with an endomorphism. That's as Frobenius, right? So, and if you have such a guy, you can produce a monoid extension. So I will produce gamma tilde, which is an extension of Z by G, and that will be the semi-direct product. Of course, any extension is a semi-direct product. So this is a normal subgroup, and this is Z. And okay, so here I have one, and the conjugation action of 1 is Frobenius, right? So if I have a group with an automorphism, you can form this semi-direct product, right? So now let's consider a geometric interpretation of So what are conjugacy classes? Let's say classes of this gamma mapping to 1. Well, so what are gamma mapping to 1? They are one-to-one correspondence with elements of the group, right? So these are just elements of the group. If I have element here, I assign to it G times 1. Right? It's an element of the semi-direct product. What happens if I conjugate this? So if I conjugate this by G prime, right, G prime inverse, so, okay, I need to, that's equal to G prime, G1, G prime, 1 inverse, G prime. Okay, 1. Yeah? So, and this is a Frobenius applied to G prime. So that's equal to G prime times G times Frobenius applied to G prime inverse times 1. So that means that under this correspondence between G and gamma mapping to 1, the conjugacy classes of gamma correspond to what's called twisted conjugacy classes in G. So G is equivalent to G prime, G prime Frobenius of G prime inverse, right? Or equivalently, these are the same as isomorphism classes of G underlying torsors over BG. Oh, sorry, over spec FQ, right? What is a torsor? Well, a torsor is a set with an action which is a torsor over G together with an action of the Galois group. Well, these two actions do not commute. They commute. They commute through this Frobenius, right? So you have the action of the Frobenius on G itself, and they commute. So that's kind of the set of conjugacy classes. It's what's called the first homology of the Galois group of FQ bar, FQ, with coefficients in G, right? So very good. So what we have in this formula, we have summation over G torsors over a point. So what is the geometric meaning of this guy, of this subgroup? If you have a torsor, you have its automorphism group. And I claim that that's precisely this. What is an automorphism of a G torsor? Well, if you have a G torsor of an algebraically closed field, its automorphism is just G itself. If you want a torsor over this, it must commute with the Frobenius, and that's precisely the condition. So very good. With this maybe realized, let's consider, let's apply this formula to do the point count on the quasi-fine stack of BG. So let's take, so assume that lambda, that's kind of the ring of coefficients, z mod L to the nz, something like this, admits. Да. Правильно, но сам торсер задается лямбда. К каждому лямбда мы сопоставляем торсер. Они будут изоморфны, если лямбда сопряжены. Но действительно, что такое торсер? Это элементы из группы по модулю вот такого скрученного сопряжения. Но мы видели, что G класса сопряженности в этих самых во множестве всех лямбда это то же самое. Как, Катя, еще раз сказать. Значит, вот допустим, что у меня есть лямбда. Но я по лямбде строю торсер. Ну, как я его строю? Значит, сейчас скажу. Значит, ну, этот... Ну, я записываю лямбда как g умножить на 1. У меня гамма — это по прямое произведение. Значит, такие гамма, они отвечают просто элементам группы. Что отвечает сопряженным гамма? Значит, вот допустим, что у меня есть две гаммы, которые одна сопряжена другой. То есть я вот беру гамма и сопрягаю с помощью G'. Мы вычислили, чему это равно. Мы вычислили, что это будет G', G Frobenius от G' в минус первой степени умножить на 1. Нет, пока я только заметил, что вот сумма здесь по G-торсеру на спектре FQ в этой формуле. И что вот эта группа, она допускает интерпретацию в терминах G-торсеров. А именно эта группа автоморфизмов G-торсера. Да, просто такая группа. А что такое след, мы пока абсолютно не обсудили. А сейчас обсудим. So let's assume that lambda admits a finite resolution by lambda g gamma modulus. So lambda, I consider lambda with trivial action of gamma. It's trivial representation. And let's assume that it has a resolution. P0, P1, and so on. Where pi are, well, they are modulus over this, but I assume that they are finite projective. Over lambda of G, right? Okay, so let's take the trace. Well, so what it means? It means that, in particular, so this is a projective resolution of the trivial representation of G, right?
G is a quotient of gamma, right?
Right. No, G is a subgroup. G... Что? Гамма это... Как это не лежит? G... Да, да. Как это не лежит? Нет, но там было еще гамма с волной. Да. Да. Что такое? Нет, но... Сейчас, да, вы... Сейчас. Сейчас. Хочу я... Сейчас. Нет, что-то я... Простите. Значит... Сейчас. То есть вы хотите сказать, что G при этом отображении сейчас. Она попадает куда? Попадает в ноль ведь. Точная последовательность. В ноль. А вовсе не сюда. Значит, сейчас. Сейчас, значит, как мне действительно хороший вопрос. Значит, сейчас. Значит, как мне... Давайте я вот так напишу. Да не будет вопроса. Хорошо? Но в том, что G действительно здесь не лежит. Ну, вот у нас есть такая точная последовательность. Мы берем прообраз. Сейчас, вы предлагаете взять pullback в качестве гаммы, pullback неотрицательных чисел. Хорошая идея. Да, то есть правильно. Можно, то есть вот давайте считать так, что это множество чисел, которые, ну, в общем, да, c больше либо равно 0. Хорошо. Тогда лежит. Да. Да.
Поэтому если мы взяли не так, то у нас будет, это не будет двуколесным.
Да, совершенно правильно. Да. Угу. Очень хорошо. Да, значит, никакой проблемы нет. Хорошо. Okay. So then, so what we have is that homology. So we can use this complex to compute homology of G with coefficients in lambda. So if I take this complex and take coinvariance, that's the same as the homology of the tensor product of lambda tensor lambda over lambda of G over G, or derived tensor product, right? That's that's because coinvariance is precisely the tensor product with lambda. And this is known as homology of group G with coefficients in lambda. Okay. And now let's interpret that formula. So, well, so the trace of over lambda z gamma of this acting on P.
But we know that this is non-zero for infinitely many I. How does this not contradict our assumptions that lambda admits finite resolution?
How do we know that this is non-zero for infinitely many I?
Because we can just induce classes from single subgroup.
Well, first of all, you get you will have well, so and so what? So you induce, so you get a classes with coefficients in induced representation. So I agree that if you have a, say, that a finite group has infinite homological dimension. But I'm not sure that homology with trivial coefficients are all necessary in infinite, in arbitrary large degrees. But in any way, so we are going in a second to assume that order of G is invertible in lambda. So at least in this case, you have only zero homology group. So, but nevertheless, so let's compute this. So what is this? This is equal, well, by definition, this is if this number is invertible in lambda, this is the trace, usual trace, divided by this order, acting on P. So this is a complex. So what I mean here is the alternated sum of traces. So I look at this complex. I look how gamma act on the terms of this complex. Well, this is a complex of, that's an exact complex. That's a resolution. So the alternated sum of traces must be equal to 0. So that means that this is equal to 1 over z gamma, trace of gamma acting on lambda itself, right? 0 term, that's a resolution. If I discard this, then alternated sum of traces will be equal to the trace. And this action of gamma on lambda is trivial, so what I get is just 1 over z gamma. So that means that the trace of, now the formula that we have here reads as follows, that the trace of 1 acting on P dot G, right? That's a complex of projective lambda modules. So by definition, you can think of this as a trace of 1 acting on this derived tensor product. Lambda of G, right? So is equal, well, it's going to be equal to this sum, right, over all conjugacy classes. And I want to write it as follows. So I take the classifying stack of this group. Its FQ points are by definition G torsors over spec FQ. These are conjugacy classes. And so but this is a stack, meaning that every point has automorphism group, and this is the cardinality, the order of the automorphism group. So I want to count the points here, but, well, so formally that's just sum of the sum over 1 over order z gamma. But somehow I want to think of this as the point count on this stack. And what you have here is a version of the Lefschetz formula, right? Ну, смотри, вот мы выяснили, что классы сопряженности вот этих гамма, они находятся в взаимно однозначном соответствии с торсерами. То есть это вот просто точки БЖ. А каждая эта штука — это как раз группа автоморфизмов. Вот как у нас в формуле там. No, that's the content of the lemma. So alternated sum of traces on homology of the classifying stack. So let's say that this is kind of trace of the Frobenius, acting on homology of the classifying stack BG lambda is equal to this. So that's kind of Lefschetz formula in a baby situation. Okay? That's homology of the group, which is by definition homology of the stack. Okay. So, well, probably it would take me another 15 minutes to finish using all this formal property, elementary algebra, Lefschetz formula, and I will do it at the beginning of next lecture, and then we will move to the Linz conjecture. The last part of so this will prove the first Weil conjecture. Then I will prove the third Weil conjecture, and then the remaining time will be devoted to Poincare duality in sort of general setting with singular varieties. So we will discuss a particular functional equation for zeta function. So this will be the second conjecture. Okay, let's stop here. Thank you. Ну, это единица. Это единица, вот это же не единица, это же не тождественный оператор, это ли образующая, да. Yes. Well, the first conjecture is for any variety, rationality, even with coefficients. And we already, well, we will finish it in tomorrow. So again, for all varieties. So the last Weil conjecture about the eigenvalues of the Frobenius only for smooth projective. There is a generalization, but we will not touch it. And then, so the second conjecture, a functional equation, can be extended to all varieties and all coefficients.